All right. Hope everyone's doing well. Let's get started. So today we're going to start chapter 3. And so chapter 3 is all about trying to determine electric potentials, V of X, Y, Z, so that we could use them to then calculate electric fields by taking the gradient of the potential, specifically the negative gradient. And so what we're going to try to do is we're going to try to solve for the potential starting from Laplace's equation. And so we're going to work out some properties of the solutions to Laplace's equation. So let's just recall Poisson's equation first. Poisson's equation is the more general one, and it says that if we take del squared of V, that's equal to minus rho over epsilon naught. This really just comes from the Gauss's law, right? Gauss's law was that the divergence of the electric field was rho over epsilon naught. So that if we write the electric field as minus the gradient of V, the divergence of the gradient leads to del squared, and the minus sign comes from the fact that we have to take minus the gradient of V. So what Laplace's equation says is, what if we had a region of space where we want to find the potential, but where the charge distribution, there is no charge in this region of space. It's a charge-free region. That doesn't mean there's no charge anywhere. There could be sources of charges, and in general, there will be sources of charges outside this empty region that's setting up the electric field that we're ultimately trying to find. But in that region where we're actually interested, there is no charge sitting there. So in a region where rho is equal to 0, this reduces to Laplace's equation, which is del squared V is equal to 0. So we'll start by working out some of these properties of the solutions in Cartesian coordinates. And so it's going to be the second derivative of V with respect to X plus the second derivative with respect to Y plus the second derivative with respect to Z has to be 0. And so this is a partial differential equation. In general, solving that is complicated. And so we'll try to develop some techniques that will help us do that. Okay. So Laplace's equation it appears in many branches of physics and math, not just in electrostatics. So, for example, if you wanted to find, it shows up in like some heat flow problems, not heat flow, probably heat distribution problems, or like, I think if you want to find the patterns on an electron head. Okay. So the first thing that Griffiths does is he says, let's consider the easiest possible case, and we're going to try to solve this in just one dimension. Okay, so this is going to be Laplace's equation in 1D. The 1D version is, as we'll see, it's almost trivial. It's very straightforward. But the reason we're doing it is because some of the properties of the solutions that we're going to find will generalize to the solutions that we see in 2 and 3D. Okay, so the strategy is to first work out some properties of the solutions to Laplace's equation in 1D, and then generalize to higher dimensions. All right. So in 1D, our partial differential equation becomes just an ordinary differential equation. It's second order, so we have to take 2 derivatives, but that's what we're trying to solve. So we integrate once, and the integral of 0 with respect to x is just a constant. I'm going to call that constant m. So this is a constant. And then if I want to find v, I integrate with respect to x again. The integral of a constant is x times that constant plus another integration constant. And so integrating again, we would get v is mx plus b, which is clearly a straight line. All right. So that's not a very interesting solution. Oh, what happened? Oh, that's nice. We'll see if this, does anybody have dry erase markers? You've got one? Okay, well, in an emergency, we'll use it. Oh, you got a whole collection. Some colors. All right, we'll see if this goes out again, then we'll switch over to the whiteboard. All right. One of the issues here is we've integrated twice, and that came up with 2 integration constants, and we need some tools to find those constants. So the 2 integration constants are determined by boundary conditions. Now, there's actually a couple ways you could go about this. You could say, I'm going to give you two values of v at two different positions of x, or I'm going to give you the value of v at one position of x, and I'm going to give you the value of dv dx at another x. So something like that. So, for example, if we know that, say, v at 0 is equal to 6 and v at 3 is equal to -3, we could sub in to our solution x equals 0. So it's going to be m times 0 plus b is equal to 6. And so we determine that b is equal to 6. Okay, I know this is simple, but let's just go through this so that we can think about this in a similar way in higher dimensions. All right, so then that means in general, v is mx plus 6. And so now we use our second condition. V at x equals 3 is going to be 3m plus 6. And that has to be equal to -3. Subtract off the 6, you get -9, divide by 3, you get m is -3. So m is equal to -3. And so therefore our full solution is v is -3x plus 6. Okay, fair enough. So what I want to do is I just want to plot that solution. So I guess I'll do it over here. Here's our x-axis, and here is v. And so at x equals 0, we end up with +6. And so over here is our 6. And then when x is equal to +3, +2, then we'll get, sorry, what am I? Yeah, okay. So where's our other boundary? Was at -3. Sorry, x was 0, and then x was 3, and we get -3 at that point. Is that right? Is that what we said? Yeah, sure. Yeah, -3. Sorry, what I've drawn in my notes is a little bit wrong, so I'm trying to fix it on the fly. 1, 2, 3, 4, 5, 6. 1, 2, 3. Here's -3. And so our other boundary is sitting over here. Okay, and so this is our solution to Laplace's equation in 1D. Okay, and what I want to notice about this are some of its properties. Nope. Okay, so note number 1. There are no maxima or minima in our solution. All of the extreme values occur at the two boundaries. In our case, x equals 0 and x equals 3. So v of x has no local minima or maxima. All extrema occur at the boundaries. It won't be as easy to see in higher dimensions, but this property is going to be preserved as we go up to higher values. We can test this. How do you test if you take the first derivative, you set it equal to 0, that finds you an extreme. How do you know if that's a minimum or a maximum? the double derivative test. And so what specifically is the double derivative test?
Awesome. It's going to be
Yeah, that's right. So if we take the derivative of our solution, which was mx plus b, we just get m. And so that's not, m's not zero, it's just some constant, some slope that doesn't change. And so this is never equal to zero. And so there are never local minima or maxima. So this is not equal to zero. And so there are no local min or max points. Okay, and just to be thorough, if we took the second derivative, then we would get zero, right? That's, this is actually Laplace's equation. And when your second derivative is equal to zero, the second derivative test is inconclusive. But we can already see that the first derivative has no zeros, so there are no minimum or maximum. So we're going to require, in general, that the second derivative is negative for maxima, and the second derivative should be positive for minima. Okay. The other thing I want to note is if we go back to our picture, and let me just pick a arbitrary value of x. And so maybe I pick a value of x that sits here. And I go up and I find the value of the function at that value of x, and so it sits here. Okay, so what I'm going to do is I'm going to go to some point x plus a. And x plus a maybe sits over here somewhere. And this is the value of the function at x plus a, right? It's a little less than the value was at x. And then I can go over here and I can find x minus a, which lives here. And this is the value of the function when x is, well, at the position x minus a. So what I want to notice is because this is a straight line, if I was to average the potential at x plus a and x minus a, they would average to b of x. And it doesn't matter how big or small a is, it's always going to be true as long as I stay between my two kind of boundaries of where the solution is valid between x equals 0 and 3. Okay, so that may not be that interesting, but let's write it down, okay? Because it's going to be another one of those properties that generalizes to higher dimensions. So note 2. The value of v at x is the average of v at x plus a and v at x minus a for any a. All right. So those are the two things that I wanted to notice about the 1D solution. So then we move on and we say, okay, what about Laplace's equation in 2 dimensions? Okay, so we're going to have now, we're back to a partial differential equation, but there's just 2 terms, like so. And Laplace's equation says that those have to sum to 0. So what I'm going to do is I'm going to do a bit of an aside here. And it's going to be slightly longer. And this is something that Griffiths doesn't do, but I have to look it up. Okay, so maybe you've done this more recently than I have. But if I ever knew any of these facts, they evaporated long ago. So finding extrema of multivariable functions. So one thing I do know is that you would take your partial derivative with respect to x, set it equal to 0, and then you take your partial derivative with respect to y, set it equal to 0. Now you have a system of two equations, and you can solve those for the points x and y that satisfy those conditions. And that's where you're going to have your extrema living. And then we want to test to know if, okay, for each of those points, is that a minimum or a maximum or a saddle point? And so I want to tell you how that test works. So I'm going to write down the procedure for finding local minima and maxima for 2D functions. All right, so the steps are: 1, if you have some 2D function, f of x and y, we find all the x, y points that satisfy, well, they have to simultaneously satisfy these two conditions. The derivative with respect to x is 0, and the derivative with respect to y is 0. Okay, and so here's the part that I didn't know, and I'm not going to prove any of this to you. There's something called the Hessian matrix. Is this something that you've ever come across? You've seen it? Okay, so the way this matrix is defined is H is two derivatives of f with respect to x, and then it's the second derivative, one with respect to x, one with respect to y, and then the same thing over here. And then this one is two derivatives with respect to y. Okay. So you take your function and you calculate that matrix. The next thing you do is that for each, for each point x, y from the first step, right? So we found those points that satisfy the first derivatives equal to 0. So for each one of those, we evaluate these derivatives at those points, and then we check the determinant of this Hessian matrix. So we get a minimum or maximum if the determinant of H is positive. Okay, well, in this example for our 2D function, I can write down the determinant of H. Determinant of H is just, well, let's see, it's going to be that first diagonal. So we're going to have d2f dx2 times d2f dy2 minus the product of the other diagonal. But the other diagonal is the same, right? The diagonal along this, I don't know, the negative slope 1. Well, in fact, I guess it's positive. Anyways, it's just the square of this thing. Okay. Now, if you think about this, we're looking for a determinant that's positive. What would you have to say about these two factors if I want the outcome to be positive, right? This minus something squared is always positive. So I'm minusing a positive number. What does that mean about this? It has to be a bigger positive. So what's the only way I can get positive? These two have to have the same sign. They're either both positive or both negative. That's the only way that this could possibly happen. So therefore, we can only get minima or maxima if d2f dx2 and d2f dy2 have the same sign. Okay, so that's an important point. We're going to come back to it. Let me just finish off this Hessian determinant. If the determinant of the Hessian matrix is negative, we have a saddle point. If the determinant of H is equal to 0, the test is inconclusive. Okay, let's go back to Laplace's equation in light of this new bit of information. So in 2D, this requires that two derivatives of f with respect to x plus two derivatives of y has to be 0. Well, what's the only way I can add up these two things and get 0?
Or they're
Yeah, they have. Yeah, so you're right. They have to have opposite signs is the important point that I want to, it's possible that both these derivatives are 0, but in general, let's imagine they're not 0. Then these have to have opposite sign, and therefore we could never get a determinant that is positive. Okay. So therefore, d2f dx2 and d2f dy2 must have opposite sign. Therefore, f cannot have extrema. In fact, it's exactly the same situation we found in 1D. All the minima and maxima will be at the boundaries of this 2D surface. So in a 2D surface, the boundary would be like some kind of line that goes around that surface. Okay. All right, so fair enough. So it turns out, I won't write it down, but if you take this Hessian matrix and then take the trace, and the trace is adding all the diagonal elements, if that trace is positive, you have a local minimum. If it's negative, you have a local maximum. Okay. Again, I'm not going to write it down, but you can generalize this to 3D. You could have a three-dimensional Hessian matrix where you have like 3 by 3. So you have two derivatives with respect to x, and then you have a dx dy, then you have a dx dz. And then you have dx dy, two derivatives with respect to y, dy dz, and so on. Then it turns out that the determinant doesn't have enough information, so you have to solve some eigenvalue problem. It generalizes. What we would always find is that for 2 and 3 dimensions, you will never have extrema, minima, or maxima in your solutions, always on the boundary. Okay, so this argument generalizes to 3D, and the conclusion is that in 1, 2, or 3D solutions to Laplace's equation contain no extrema except at the boundaries. Okay, so that's one of our conclusions. All right. So the other thing we saw in 1D is that if I was to take this average of values just on either side of x, they equal the value of x. That also generalizes. And I want to see if we can see how that works in 2D. So in 2D, we can picture the solutions to Laplace's equation by considering a wavy line cut around the perimeter of a box. Then we stretch a rubber membrane over the box. Okay. The shape of this membrane gives solutions to Laplace's equation. And generally, the solutions to Laplace's equations are called harmonic functions. So if you see people talking about these so-called harmonic functions, what they're talking about are solutions of Laplace's equation. Now, Griffiths has a nice picture, and I think I can find that picture for you. I think it's this, no, that's the next set of notes. Right, let's see if I can find, here it is. Let's see if I can copy this thing. Copy, I hope that worked. And let's see if I can paste it. There we go, good. Okay, so here's the box. And so you go around with a pair of scissors and you cut out some wavy line around this, and then you stretch over this membrane. And if you look at this, you can see the boundary here is this line that goes around the perimeter, and that's where the maxima is. And you can get these little local minima along this boundary, but everywhere in here, you're going to get something that it's not necessarily a straight line. In general, it's not a straight line, but it does not go through minima or maxima. It always has the same curvature as you go along some straight direction. All right. So what we want to do is we want to come up with this averaging argument in 2D. So if we're going to call this note 1, then our note 2 is the following. If you draw a circle of radius r around the point xy, the average of the around the, well, okay. Let's say the average of v of xy around the circle is equal. I don't like this. So the average of v around the circle is equal to v at the point xy. Okay, and so what this picture is trying to do is to show you that fact. Now, it may not be completely obvious because we have here some point that like on this part of the circle is quite high, and then over here it's quite low. So how is it that this point in the middle, which is closer to the low side, averages to the value around the circle? What is the argument for that? How is it possible that if I average the potential around this circle, then I get the value? It's because this point over here, we have high values of the potential, but it's over a short section of the circle. But over here, we have low values, but it's low values that are similar to the value in the middle, except they extend over a large part of the circle. So that in general, you're only adding up a small number of really high values, and you're adding up a large number of smaller values, such that the result is something closer to a smaller value. So what we have here is high values of the potential over a short section of arc. Whereas here we have small values of V over a long arc. Okay, so if we were to write down this average, well, how do you average functions? You take 1 over the length, and if I'm going to go around this circle of radius r, the circumference is 2 pi r, and we'll integrate around that path, and we'll take all of the v values around that circle and add them up. And this integral is over a circle of radius r. So in this picture, you can see the circle of radius r is projected down into that xy plane. So that's the circle of integration. And it doesn't matter what the radius of that circle is. It could be a small radius, a large radius, as long as it's defined in our region of our solution, this will always work. Okay, so this means that v of xy is equal to the average of v around the circumference of the circle. All right, so that's our second note. Okay, so now we move into 3 dimensions. So Laplace's equation in 3D. And you could probably guess what our notes are going to be. Note number 1, v of x, y, z solutions have no extrema. Okay. And that's just a generalization of that Hessian matrix type argument that I'm not going to try to do. The second note is that, so instead of placing a circle around our point xy, we're going to place a sphere around our point xyz. That sphere has radius r. If I average v of x everywhere over the surface of that sphere, it has to equal the value of the potential at the center of the sphere. And we'll do a proof of that one. So the value of v at x, y, z is equal to the average of v over a sphere of radius r with the point x, y, z at the center of the sphere. Okay, and so mathematically, we could write that as the potential at x, y, z is, so we divide by the surface area of our sphere, and then we add the potential up around that sphere. And this is a sphere of radius r. All right. And so I'm going to try to prove this second note to you. So proof of 2. All right. So we're going to do it for a point charge. So we'll consider a point charge Q on the z-axis. And we want to find V at x, y, z is equal to 0, 0, 0. Well, if the point charge is at position z, well, I know what the potential of the point charge is. What I expect to find is that V is 1 over 4 pi epsilon naught Q divided by the distance from the point charge to our origin. And so if it's just sitting on the z-axis, it's whatever, this is what we expect to get. So we're going to try to do the averaging routine for our circle and see if we get that answer. So let's draw the picture. Here's going to be our z-axis. We'll have our y-axis here, and here's x. All right, Q, our point charge is sitting here. And then, I've got a circle of radius r that sits something like this. And so here's some point on that circle. This is length r. What we have here is our r prime is from the observation point to our source charge. And so this sits at position z. And then we have the distance from our source to where we're calculating the potential. So we usually call that like the little script r. Okay, and so this black line is our sphere, like so. All right. So we're going to say that inside the sphere, rho is equal to 0. And so therefore, we're going to try. So we've satisfied this Laplacian. All right. So we know that the potential is 1 over 4 pi epsilon naught Q divided by the script. Okay, that's the potential at that point on the sphere that we've drawn. So I'm going to try to draw this triangle we have. We had a distance z to Q. And so here's our origin here. And then we go out to some point on the sphere, and that's sphere is radius r. And then I want to know the length of this thing. And so I'm going to call this angle theta is this angle theta in our spherical coordinate system. So how can I relate these lengths to one another? It's not a right angle triangle, so what do I have to use? The law of cosines, yeah. Law of cosines. So the law of cosines says that if I want to know the length of the side opposite of the angle, the square of that length, It's given by z squared plus r squared minus 2zr cos theta. All right. Well, that means the potential is 1 over 4 pi epsilon naught q over the square root of all of this stuff. So z squared plus r squared minus 2zr cos theta. All right. And what we're going to try to do is we're going to try, so this is our potential at a point on the sphere. And we're going to try to calculate the potential at the center of the sphere using this method where we divide by the surface area of the sphere. And then, let's see, we've got some constants, q over 4 pi epsilon naught. And then we're going to integrate over our sphere. So we have 1 over all of this stuff, z squared plus r squared minus 2zr cos theta. And then we have to integrate over the surface of the sphere. The sphere is at a constant radius r squared. And so we're going to have a d phi and a d theta. The d phi integral is trivial. There's no phi in here, so that just gives us a factor of 2 pi. Okay, and in fact, we can cancel these r squareds. When I do the phi integral, the 2 pi partially cancels with this 1 over 4 pi. So we're going to get a 1/2 q over 4 pi epsilon naught. Now we have the integral of theta equals 0 to pi. And, oh, what did my dA is wrong, right? What am I missing? Sine theta, exactly. You're right. Okay. I want that sine theta in here, actually. So we're going to have sine theta d theta square root of z squared plus r squared minus 2zr cos theta. All right. So we're going to make the substitution. U is z squared plus r squared minus 2zr cos theta. So du is going to be, let's see, we take the derivative of cos, we get minus sine, right? So it's 2zr sine theta d theta. And so therefore, our sine theta d theta is going to be du over 2zr. All right, yep. Oh, yeah, that's just from here. So we're adding up all the potentials times like little patches of area on our sphere. And then to get rid of that area, we have to divide by. Yeah. Okay, so the next little insight in order to make this easier is we're going to say when theta is equal to 0, u is equal to what? So theta is 0, cos theta becomes 1. So we get z squared plus r squared minus 2zr. What's a nicer way of writing that? Yeah, something like that. It doesn't matter if it's z minus r or r minus z. And so when theta is pi by just pi, then u is going to be z squared plus r squared. Now cos of pi becomes minus 1, so we get plus 2zr. And so that one is z plus r squared. Okay, so let's put this substitution in our integral. So when we replace sine theta d theta, we're going to get a 1 over 2zr. So we'll have a 1 over 4 ZR, because I already had a 1/2. And then we'll get a Q over 4 pi epsilon naught. That doesn't go anywhere. And so now we have the integral from U is Z minus R squared to Z plus R squared. And then I think it's just U to the minus 1/2 du, I think. Good. All right. And we're almost done, actually. So we integrate the minus 1/2 power becomes a plus 1/2. So we have to divide by 1/2, which is same as multiplying by. So we're going to get a 1 over 2 ZR Q 4 pi epsilon naught at U to the 1/2 at Z minus R squared and Z plus R squared. Okay. So 1 over 2 ZR Q over 4 pi epsilon naught. And so let's see. It's going to be Z plus R, because we're going to take the square root, minus Z minus R. Okay, so the Z's are going to cancel, and we end up with a 2R, and overall we get Q over 4 pi epsilon naught Z, and this is what we expected. This is point charge, distance Z away. Okay, now you might say, well, that's not really a proof. All you've done is you've shown that it works for a point charge. What if our potential was due to some complicated arrangement of charges or some complicated charge distribution? Well, I can always take any arbitrary charge distribution and I can construct it by placing a bunch of point charges and then adding them all up. Because the potential follows or obeys the superposition principle, if this argument works for a single point charge, it works for any collection of point charges that can be used to make any arbitrary distribution. So we can treat any distribution of charge as a collection of point charges that, well, obey the superposition principle. Therefore, this proof generalizes to any row. All right, good. So all of this, really, the two things I want you to take away is that when we solve the Laplace's equation, the solutions that we're always going to get will have the two following features. They have no extreme points, and they have to obey this averaging rule that you take either an interval around some point or a circle around the point in 2D or a sphere around a point in 3D. And if you average around those shapes, you'll get the value at the center. All right. So the next thing we're going to do is we're going to talk about some uniqueness theorems. And what these uniqueness theorems are going to say is, if you're given some set of boundary conditions, so you know the potential on some boundary that surrounds a region of space, and you find a potential that one satisfies Laplace's equation, so this del squared V is equal to 0, and satisfies the boundary conditions, then you're guaranteed 100% that that potential is a solution, and it's the only solution. It's the unique one. So I'm going to first just write down the first uniqueness theorem. First uniqueness theorem. Okay, what it says is the solution to del squared V equals 0 in a volume. I have to be careful here. I'm trying to write like a script kind of V. So our volumes are going to be the script V, and it's not to be confused with this regular capital V, which is potential. So the solution to Laplace's equation in volume V is uniquely determined if V is specified, specified on the boundary of the surrounding surface S. All right. So in other words, there's only one solution for V that satisfies Laplace's equation and the boundary conditions. So the proof is kind of neat because it's short, okay? And it's kind of clever. So let's suppose the way that this proof is going to go is we're going to assume that there's a counterexample where we can find two solutions that satisfy Laplace's equation and the boundary conditions, and then we'll show that those two solutions have to be identical. Okay, suppose there are two solutions such that, okay, the first solution is V1, and it has to satisfy Laplace's equation. And there's a second solution, V2, that also satisfies Laplace's equation with both V1 and V2 satisfying the boundary conditions. Okay, so what we'll do is we'll consider a potential V3 that we construct by taking the difference of V1 and V2. Well, what does that mean? So what are the values of V3 going to be on the boundary then? If V1 and V2 both satisfy the boundary conditions, that means they're equal everywhere on the boundary. So what's that difference equal to? 0. So this must have the value of V3 equals 0 on the boundary. Okay, so this implies that V3 is 0 everywhere on the boundary. Okay, well, the other thing we can do is we can say, well, okay, the Laplacian of V3 is just the Laplacian of V1 minus V2, which is del squared V1 minus del squared V2. But we started by assuming that these were both solutions to Laplace's equation, so there has to be 0. All right, so we know that V3 is 0 everywhere on the boundary, and it's a solution to Laplace's equation. So therefore, V3 satisfies Laplace's equation. All right. If it's zero everywhere on the boundary, what must V3 be inside the boundary?
Zero.
Why?
Um, because that's the average of all the, or not the average, but yeah.
Yeah, that's right. So our solution cannot have any extreme points except on the boundary. But if the boundary is zero everywhere, that means the minimum of V is zero and the maximum of V is zero. And so the only possibility is that V3 is zero everywhere. Okay, so since the V3 has extrema, let's say min and max values of zero at the boundary. Property one, or note one, requires that V3 equals zero everywhere. Okay, but V3, we built V3 by saying it was the difference between V1 and V2. And now we're saying that V3 has to be zero. And so that implies that V1 is equal to V2. And so the solution is unique. We can't construct a second solution. So what this tells us is that when we find a solution that fulfills Laplace's equation and the boundary conditions, it is the only possible solution. So it doesn't matter how you got it. You could have just guessed out of kind of blind luck, and you find, oh, it satisfies Laplace's equation and the boundary conditions. It must be the solution. There's no way around it. All right. We can extend this a little bit, and we could say if rho is not equal to zero in the volume V, so that's that script V, then we would say, well, okay, in that case, it's not Laplace's equation that we have to work with, it's Poisson's equation. And so our two assumed solutions would take on this form, and we could say, therefore, if V3 was equal to V1 minus V2, then we would say del squared V3 is going to be del squared V1 minus del squared V2. It's still going to be zero because these rows are just going to cancel and the argument is exactly the same. So we again find that V1 is equal to V2. So therefore, even if we have a region of space where the charge density is not zero and we have to use Poisson's equation, this uniqueness theorem still says that the solution is unique. Okay, so we could write that down. Corollary to the first uniqueness theorem. All right. The potential V in volume script V is uniquely determined if the charge density rho in V and the value of V, the potential on all boundaries are specified. Good. So there's a second uniqueness theorem. We're trying to get through all of these kind of little details so that we can actually start solving potentials. So I don't know if we'll finish this second uniqueness theorem, but let's give it a shot. We'll start it anyways. So 3.1.6, conductors and second uniqueness theorem. So the geometry is going to be the following. We're going to have a volume of space, script V. So we have a region of space V bounded by a surface S. Okay, and so here's my surface. And here is my volume V. So what we're going to do is we're going to place some conductors inside of our volume, and we're going to put some charge on those conductors. We're not going to say anything about how the charge distributes itself on the conductor. We're just going to tell you what the total charge is. Okay, so inside the volume, so we're going to assume that rho is known. So there is, in general, some charge that lives in this volume, and there are conductors, which I'll draw red, with charge Qi on their surface. All right, so we'll have a conductor over here, and we'll say its charge is Qa, and then we have another conductor over here, it has charge Qb, and you could put as many as you want. The only other thing that I'm going to specify is that this surface that surrounds our volume is either a conductor or it's out at infinity. So the volume V is either unbounded, i.e. infinite. If it's infinite, then the potential out at infinity is defined to be zero. So it'd be zero potential out at that infinite surface, or it's surrounded by a conducting surface S. Now, one of the properties we know about conducting surfaces is that they're at a uniform potential. So the potential may not be zero, but it's constant. Okay, and in either case, unbounded surface are one that's surrounded by a conductor. So in either of these cases, V is constant on the bounding.
That's potentially.
Yeah. Okay. So what can we do with this? So I'll write down what the second uniqueness theorem is. So second uniqueness theorem. All right. So in a volume script V, containing conductors and a specified charge density rho, the electric field is uniquely determined if the total charge on each conductor is given. Okay, now the proof of this is a little more involved, but let's see how much progress we can make. Okay, we're going to do the same thing. We're going to assume that there are two electric fields that satisfy these conditions, and we're going to prove that they must be equal to one another. So suppose E1 and E2 are possible. All right. Well, what do we have here? What we're going to do is we're going to apply Gauss's law, and we have a differential form and we have an integral form, and we're going to use both of them. The differential form involves this charge density rho, and when we do the integral form, we'll place Gaussian surfaces around these conductors one at a time, and let's see what happens. So in between conductors, each electric field, our E1 and E2 solutions, must satisfy Gauss's law in differential form. Okay, so Gauss's law is the divergence of E is equal to rho over epsilon naught. And so this has to hold for E1 and E2. Okay. They also must satisfy the integral form. And specifically, we're going to go around each conductor. All right, so let's go back to this picture and let's just pick an arbitrary one of these conductors. I'll pick conductor A here that has charge QA. And this is my Gaussian surface. And I can draw one of these for each of the conductors that we have. Okay, what is the integral form of Gauss's law? Well, it says that this E1 dot dA must be Q enclosed over epsilon naught. But Q enclosed is just going to be whatever charge is on whichever conductor we're sitting beside. And so this integral is around a surface that surrounds conductor I. And then, of course, E2 must satisfy the same thing. All right, fair enough. We can take another Gaussian surface and we can place it just inside the conductor that encloses the entire volume. Or if we want, this could be out at infinity. Okay, so here's another Gaussian surface. All right. For a Gaussian surface, just inside the surrounding boundary, well, okay. So E1 dot dA, it just has to be this total enclosed charge, right? It would just take all the charges on all of the individual conductors plus integrating over that charge density that's in that volume. You add all those things together and it just sums up to some total charge. And same thing for E2. Okay, and so this is on the outer boundaries. All right. So like before, what we're going to do is we're going to examine E3 is equal to E1 minus E2. All right. So if I do that, what's the divergence of E3? Well, E1 and E2 have the same divergence, so that when we take their difference, we're going to get 0. This is equal to 0. Okay, we're going to come back to this thing in just a little bit. And if we did this type of calculation, it doesn't matter if we do it for the outer surface or if we do it for an individual conductor. Since E3 is E1 minus E2, it's going to be QI minus QI, or it's going to be Q total over Q total. Either case, it's going to be equal to 0. And this is for all boundaries. All right. So let's see. Can we actually finish this? Let's see if we can finish this. Yeah, maybe we can. If you let me take a couple minutes, I usually don't do this. Okay. It would be a shame to have to redo all this Wednesday. So next, consider this divergence of the product of the potential and E3. It's not obvious why we want to do this, but what we're going to do is we're going to apply product rule number 5. So if you go to the inside cover of Griffiths, you'll see a product rule for the divergence of a scalar times a vector. And what it is V3 times the divergence of E3 plus E3 times the gradient of V3. All right. So divergence of E3. We already said that that has to be 0. What's the gradient of V3? What's the gradient of a potential? No, the gradient of a potential is the electric field. It's minus the electric field. That's right. So what we end up here with is the divergence of V3 times E3 is equal to minus E3 squared. Okay, so we have E dot minus E. Okay, so that means if I integrate this funny quantity, that must be equal to minus the integral of E3 squared d tau, right? Because we said that was just equal to minus E3 squared. But this is the divergence of an integral over some volume. And so we can, by the divergence theorem, express this as a surface integral. So this is the integral over all surfaces of V3 E3 dot dA, and this is a divergence theorem. And that must be equal to minus this volume integral. So, okay, we're almost done. All of the surfaces that we have are all conductors. We have this conducting surface, and we have all of these conducting surfaces. And everywhere on a conducting surface, the potential is constant. Okay, so all surfaces are next to conductors where V is a constant. Therefore, V3, whatever it is equal to a constant. And so that means I can take it outside the integral. And so therefore, what we're left with is V3 E3 dot dA is equal to minus this volume integral of E3 squared d tau. Well, we said this surface integral has to be 0. Let's call this equation star. And so this is equal to 0 by star. And the only way that this volume integral can be 0 is if the electric field is 0. And so therefore, E3 is equal to 0. But since E3 is equal to E1 minus E2, and now we're saying that has to be 0, it follows that E1 is equal to E2, which means there's one and only one unique solution. Okay, so I know that was a bit of a grind, but we've done like a lot of this mathematical groundwork where now we have these tools and we'll be able to use them to help us calculate some potentials. And that's really what the rest of the chapter is dedicated to. All right, good. Thank you very much. And we will see you on Wednesday.